Good day, BS Chemistry students. This is the final lesson for your Mathematics Analysis 1 during this quarantine season. Our last topic is on techniques of integration, and we have two subtopics. The first is integration by substitution, and the second is integration by parts. Hopefully, by the end of this lesson, you would not be as confused as these mean. So you would learn when to use integration by substitution and when to use integration by parts. The first topic is indeed integration by substitution. So let's look at what integration by substitution is. If you would be able to recall from our lesson on chain rule for the derivatives, so we are given a function u. Basically, u here is composed of x's, so you can have your 2x plus 1, 3x squared plus 4x minus 5, anything. It is put inside a parenthesis, and then there is a power, an exponent n. So if we are going to get the derivative of that, we get n times u to the power n minus 1, and then we multiply the derivative of whatever is inside the parenthesis. So this du represents the derivative of that function inside the parenthesis. Now, so basically, if we are going to get the integral of a function u raised to a certain power n, if it is appended by its derivative du, then we can get the integral by writing u to the power n plus 1 all over n plus 1, and then of course we add c as mentioned in our previous lesson. So this looks very much the same as the general power rule from the first lesson. The only difference here is that instead of just x, what we have here is u, which is again a function of x. So it can be, as I mentioned, can be x plus 1, 3x squared plus 4x plus 2, something like that. And it is very much important that we would be able to find this du. That is, the derivative of u can be found in that integral. If ever we could not find du, we should try to find a way to make it appear, if possible. So let's get into the first example. So let's say we have the quantity 3x plus 1 squared dx, and we are going to find its integral. So in here, we can see that our u, the one inside the parentheses, is 3x plus 1. So if we assign that as our u, then the derivative of 3x plus 1 is 3. And then because we are getting the derivative with respect to x, then we just write here dx. Now notice, as I mentioned before, 3dx, the du should be found in the integral. But because it is not there, then naturally what we need to do is multiply by 3. However, if we multiply by 3, we are actually changing the expression. So it's larger 3 times. So what we need to do is to find a way to transform the integral into something that would have the du but still equal to the original expression that we have. So instead of just multiplying by 3, we multiply by 3 and 1/3. Because if you multiply 3 and then multiply by 1/3, that's actually multiplying by 1. And as we know, any number multiplied by 1 is just the number itself. So how would it look like? We would transform the original expression here into this. So we will put 3dx. We want to have a du 3dx, so we put that here. And then we want to not change the expression, so we balance it out by multiplying also 1/3 here. Now remember, 3x plus 1, this is our u, so we change the entire thing into u. the exponent is still squared. And then 3dx here, as we wrote here, 3dx is du. So what we have essentially here is u squared du. Now, if we recall the lesson from the previous lesson, this can be easily integrated into u to the power 3 over 3, and of course we have the 1/3 here, so we also copy that, and then we add c. So if we simplify that, we multiply the two threes at the denominator. So we will get 1 over 9 u cubed plus c. However, we started here with an expression that is composed entirely of x. So we must be able to revert it back into x. That would be easy. What we now simply do is change this u back into its original function of x, so which is 3x plus 1. So what we have there now is 1 over 9 multiplied to the cube of 3x plus 1, and then still we add c. And that is the final answer. So we can still, just like what we did in the first lesson, we can still check if our answer is correct by getting the derivative of that. So again, we will be applying the chain rule in finding the derivative. So if we have this expression, we're going to find the derivative. Recall that what you do, the exponent, you multiply it as a coefficient. So we bring down the coefficient 3 here. So what we get now is 3 over 9, and the u will be unchanged, 3x plus 1. However, the exponent will be subtracted by 1, so that's 3 minus 1, that's 2. And then we multiply the derivative. The derivative of 3x plus 1 is 3. So if we multiply all the constants, we have 3 here and 3 here. So 3 times 3, that's 9, divide by 9. So they basically cancel each other out. So what we are left is 3x plus 1 quantity squared, which is the original expression that we have in the given. So basically, our answer is correct. Let's have another example. So let's say we have this. We are going to find the integral of 2x multiplied to the cube of x squared plus 1 dx. So again, what we would be using here as u would naturally be x squared plus 1. So if that is our u, then the derivative of that would be x squared. The derivative is 2x, and then 1, of course, will become 0. So that's 2x dx. So if you see, 2x is now already in the original equation or in the original expression. It's just that it's put here before the u. So we can simply rearrange that because multiplication is commutative. So we can put the 2x beside dx. So these two are equal. So we now have our u here, and we have our du, so we simply transform. There's no need to multiply anything because we found the du that we want, which is 2x dx. So it's already here, so no need to multiply anything. So we simply substitute our u, so we get u cubed. So again, x squared plus 1, that is u. The exponent remains the same, 3. 2x dx is the entire du. And as what we have discussed in the first lesson, this can be easily integrated into u to the power 4 all over 4. And then we add c, and then substitute back the value of u, or we can rewrite that as 1/4 u to the power 4 plus c, and then do the substitution. So we got 1/4 multiplied to the quantity x squared plus 1 to the power 4 plus c. And then we can still check the derivative of our answer, again using chain rule. So the exponent 4, multiply that to 1/4, so we get 4 over 4. X squared plus 1, the exponent will be reduced by 1, so from 4 it became 3. And then we multiply the derivative of the entire thing inside the parentheses. So derivative of x squared plus 1 is 2x. 4 over 4, this is just equal to 1, so we can simply take that out. And then it would look more elegant if we write 2x first before x squared plus 1 cubed. So final answer is this one, which is the same as what we had in the given. So our third example is the integral of the square of 2x squared minus 4x minus 3 multiplied to the quantity x minus 1 dx. So the most natural candidate here for u is the one inside the parenthesis with an exponent that is not equal to 1. So the most natural candidate for u here would be 2x squared minus 4x minus 3. So if we choose that as our u, then the derivative is 4x minus 4. So 2x squared, derivative is 4x, minus 4x, the derivative is minus 4. The derivative of minus 3 is 0. And what we have in the given is x minus 1, but what we got is 4x minus 4. So we can try factoring out 4. So we get 4 multiplied to the difference of x minus 1. So just like with the first example, what we want is to have 4 times x minus 1. So what we will be doing is we will be multiplying 4 and 1/4 to our expression. So from the original given, we will now have 1/4 times the square of 2x squared minus 4x minus 3 times 4 times x minus 1 dx. So again, this is just the same as this because what we multiplied is 4 and 1/4. So that's just equal to 1. And so this whole thing is our u. So that will become u squared. And 4 times x minus 1 dx is our du as we have written in here. So we get the expression 1/4 and the integral of u squared du. We can use now the general power rule. So we will get 1/4 times u cubed over 3 plus c. If we multiply the fractions, then we will get 1 over 12 u cubed plus c. Substitute back the value of u, so we get 2x squared minus 4x minus 3 to the power 3 plus c. And if we get the derivative of that, again using the chain rule, then we would get the original expression. Okay, so one of the uses or applications of integration by substitution is when we are using exponential and logarithmic expressions or logarithmic functions, exponential and logarithmic functions. So if we have an e to the power u, again u here is a function of x, and as long as there is an appended du, basically the derivative of the one here, then we would be able to integrate that, and its integral is simply e to the power u plus c. If you would recall our derivatives of exponential functions, so e to the u, the derivative of that is e to the u du. So if we get the derivative of this, it is simply this. Now, if you would also recall from the previous lesson, if the exponent is not equal to 1, then we were able to do the u to the power n plus 1 all over n plus 1. So this is now the case wherein the exponent is equal to -1. If we have a -1 in the exponent, then that simply becomes the ln, or the natural logarithm of u. Now, what are these lines? These lines indicate that we are getting the absolute value of u. What does it mean by absolute value? That simply means that we are getting the positive equivalent of whatever is inside. For chemistry students, I think you have, if you have already discussed getting the pH of your chemicals. So given the, I think the molality or molarity of your chemical, then you can get the corresponding pH by getting the natural logarithm. And if you have tried getting the natural logarithm of a negative number, it will give you an error. So to make sure that we will not be getting an error, we simply put an absolute value so that we would always get a positive number. And also, if you recall our derivatives of logarithmic functions, the derivative of L and U is 1 over U du. So u to the power negative 1 is simply equal to 1 over U. So again, if you get the derivative of this is 1 over U du. Let's go to some examples. So let's say we have e to the power 4x dx. So of course, the u here is the exponent of e. So the derivative of 4x, of course, is 4 dx. We already have dx here. We don't have 4, so we will multiply 4 and 1/4. So we will rewrite the integral as 1/4 integral of e to the 4x times 4 dx. So 4x now is u. So 4x has been transformed into u or substituted to become u, and 4dx has now become du. And going back to the formula, so e to the u du will simply be the integral of e to the u du will simply become e to the u, and then we add c, and of course the 1/4 will remain. And again, as always, we would not leave it as a u. We have to substitute back the the function of x value of u. So we would rewrite it as 1/4 e to the 4x plus c. And again, if we will get the derivative of this, so 1/4 e to the 4x. So if this is our u, so we would rewrite that as e to the 4x times the derivative of 4x is 4. 1/4 and 4 will cancel each other out, so we get e to the 4x, which is the one in the given. Another example, so what if we have the quantity 3x plus 2 multiplied to e to the power 3x squared plus 4x minus 2 dx. So again, the candidate here for our u is 3x squared plus 4x minus 2. So if that is our u, then our du, the derivative of this, 3x squared will become 6x, 4x will become 4, and negative 2 is 0. So we get 6x plus 4. But what we have here on the given is 3x plus 2. So what we can do is to factor out 2, so that we would see that we have 3x plus 2. So just like always, we would be multiplying 2 and 1/2 to our original expression. And so we will be able to rewrite it as 1/2 integral of 2 times 3x plus 2 times e to the power 3x squared plus 4x minus 2 dx. And again, just to be clear, so we would write, we would commute e to the 3x squared plus 4x minus 2 and 2 times 3x plus 2 dx, so that we would have e to the u, and then this one is du. So we would be able to rewrite it now as 1/2 integral of e to the u du, which would become 1/2 e to the u plus c. Substitute back the value of u, so we would have 1/2 e to the power 3x squared plus 4x minus 2 plus c. And if we get the derivative of that, then we would be able to get the original expression in the given. So let's now have x, the integral of x to the negative 1 dx. So this in the first lesson could not be integrated. But now that we have the techniques on integration, so we can now integrate this. So what we have here is that x will now be treated as our u, and of course the derivative of x is just dx. And so we have the integral of u to the -1 du. So as was given in the formula, so we have the natural logarithm of the absolute value of u plus c. Substitute back the value of u, which is x, so that is ln absolute value of x plus c. This might have been unnecessarily complicated or long. We could just have simply written it as ln x right away, no need to substitute u, but I was just trying to emphasize here the process of getting the integral of a function that is raised to the power -1. Let's have another example. So we have here, it may look at first a bit complex. You might be intimidated by this given. So we have 6x squared minus 3x plus 1 all over 4x cubed minus 3x squared plus 2x minus 1 dx. So yes, it can really be intimidating, but just recall all the lessons that were given to you, and you would be able to handle this. So what do we need to do here? So check, uh, there is no function inside a parenthesis with a certain power. So we would not be able to use the technique from earlier. But if we have a denominator, that automatically becomes a function to the power -1. So we can use the denominator as our u. So 4x cubed minus 3x squared plus 2x minus 1 is our u. So our du, or the derivative of this, will be 12x squared minus 6x plus 2 dx. Now, the one in the numerator, 6x squared minus 3x plus 1, is twice this, or that is half of this. So 12x squared minus 6x plus 2 dx can be rewritten as 2 times the quantity 6x squared minus 3x plus 1. So we can rewrite our integral as this, 1/2, because we wanted to have here 2. So to balance it out, we would write 1/2, and then we write 2 here. Or we can rewrite it as this. Sorry for the typographical error, there should be a 1/2 here. So this is 4x cubed minus 3x squared plus 2x minus 1 to the power -1 times 2 quantity 6x squared minus 3x plus 1. So this would now be taken as our u to the power -1, and this is our du. And using the formula, this would become 1/2 natural logarithm of u plus c. And substitute back our value of u. So that is 1/2 natural logarithm of the absolute value of 4x cubed minus 3x squared plus 2x minus 1 plus c. And we can still do the checking. For that, we can find the derivative, and we will be able to get back the original expression. Now go to the second technique in integration, called integration by parts. So with integration by parts, the integral would be divided into two parts. One will be assigned as a u, and then the other, which will be appended by the dx, will be assigned as dv. If we are able to write them as a u and dv, a product of u and dv, then we would be able to rewrite it as uv minus the integral of v du. So basically the goal here is to find an appropriate u and appropriate dv and be able to write it in this format. Usually this is done because the original given is quite complicated, wherein integration by substitution could not be done. However, if we write it in this format, then this part, this integral here, can be solved by either simple integration or the general power rule or by integration by substitution. Let's have our first example. Let's say we are going to find the integral of x times e to the power x dx. So say if you would first look at this, this cannot be integrated using the original, the formula that was given for the exponential functions. If you treat the exponent here as u, so u would be equal to x. The derivative is already dx. However, you still have an extra x here. When we are going to use integration by substitution, all of the components of your integral must be accounted for. However, in this, this x here would be an extra one, and so integration by substitution cannot be performed. So we will be doing integration by parts. So what we can do here is assign e to the power x as our u, and then the remaining x and dx will be assigned as our dv. Now, if we go back to, if we look at the formula for the integration by parts, what we needed are u, du, dv, and v. So from u, if we get the integral of u, we will be able to get du. And if we have dv, if we get the derivative of u, then we will be able to get du. And if we have dv, if we get the integral of dv, then we will be able to get v. So again, our u is equal to x, so the derivative of that is dx. Now, if we assign e to the x dx as our dv, if we get the integral of both, so the integral of dv is v, and the integral of e to the x dx is e to the x. And then note, we do not add yet our c here because integration by parts, we will be doing another integral, that is when we add c. So again, we have here our u, our du, our dv, and v. So we will now be rewriting this into the form uv minus the integral of v du. So again, our u, x here, and then v. So this is u, v, minus the integral of v du. And if you would now look at this integral, this is now easy to integrate by just using the formula for the integral of exponential functions. So if we solve that, the integral of e to the x dx is simply e to the x. Now this one here, we will not be integrating this. This is already as is. So we get x e to the power x minus ex plus c, and it would be more elegant if we would factor out e to the x, then multiply it to x minus 1 plus c. Question: can we choose our u differently? And the confused math lady is showing itself. So can we really do that? So let's say we have chosen our u as e to the x. So the derivative of that, the derivative of e to the x, is still e to the x dx. So the v would have been x dx. And the integral of that is x squared over 2. So if we form our uv minus integral of v du, then this is what we would be getting. This part here, it's not a problem. We can simplify this. However, if we look at the integral on this far right side, what we get is x squared over 2e to the x. This is even more complicated than the original integral. So with this, we can say that this is an um, incorrect choice for our u and dv. Um, with time, you would be it would be intuitive for you to choose the appropriate U and DV. For now, you might have to do trial and error. That is perfectly fine. Other lessons in math also do trial and error. If you remember your factoring, you do trial and error. So the same with this one. You do trial and error, but as you get used to it, just like with your factoring, when you get used to do factoring, then it becomes intuitive on what you would be choosing as our U and your DV. Okay, so let's have the next example. So if we are going to get the integral of x multiplied to the square root of x plus 1 dx, then the candidate for u would be x, and candidate for dv would be the square root of x plus 1 dx. So if u is equal to x, then our du would be dx. If our dv is square root of x plus 1 dx, then the integral of that. Now this one here cannot be integrated right away. We would now have to perform integration by substitution, so that we can integrate this. So we are going to choose, because we have already used u and v, so we will be using the letter w. So w will be the one inside the square root, which is x plus 1. And then if this is our w, then the dw is just dx. So square root can also be written as to the power 1/2. So we can rewrite our integral dv as the integral of w to the power 1/2 dw, and the simple general power rule would give us w to the power 3/2 all over 3/2, or that is simply 2/3 of x plus 1 to the power 3/2. So the denominator here, when we rewrite it, the 1 in the denominator will become a numerator, and the numerator in the denominator remains as a denominator. And so we would be able to rewrite our uv minus integral of v du. So u is x, our v is this 2/3 times x plus 1 to the power 3/2 minus the integral of our v, this is our whole v, and du is just simply dx. Let's go to the next slide to continue the solution. So we rewrite that, and we simplify, or we arrange this one. So we put the constant coefficient here to the left, and then we would have x times x plus 1 to the power 3/2. Now this one here, we can again integrate by substitution. So we have used u, v, and then w. You can use any letter, but we'll try to stick to those letters there and avoid using x, y, and z. So maybe we can try the letter t. So x plus 1 will now be assigned as t to the power 3/2. And then integrating t to the power 3/2, we will have t to the power 5 over 2 all over 5 over 2. Simplifying that, so we will have 2/3 times 2 over 5. And then the t was substituted back as x plus 1. So 2 times 2, we got 4. And then 3 times 5, we got 15. And so this is the final answer. Our lesson, I hope you were able to learn. If you have any questions, just reach out to our group chat. Have a good day.